Hello and welcome back to Human Physiology, and this time we're going to be looking at macromolecules. This is the second part of our basic chemistry review, and we've really looked at the atoms, we've looked at how atoms bond, whether it be through ionic bonding or covalent bonding, and we've even looked at hydrogen bonding between water molecules and other things. So that led us on to talking about acids and bases, so we know a little bit about that and the importance within the human system, such as blood and the maintenance of pH of the blood. Now we can actually think about what we're made of and what we use to continue making new parts of cells and maintaining cellular life. Because we are alive at the cellular level. The cell is the basic unit of life, and we are composed of trillions of those cells. Interestingly, and we'll talk about it throughout the course, particularly when we get to digestive, etc., there are more bacterial cells on us and in us than human cells. So the vast majority of these bacterial cells are good for us, and we need to maintain them too. So how do we do that? Well, we maintain the building part structures of the cells themselves, and that's the macromolecules. Macro meaning big, and molecule, what we've already talked about, is atoms joined together. And in this case joined together by either polar covalent bonds or non-polar covalent bonds. So there's four major macromolecules: carbohydrates, lipids, proteins and nucleic acids. So in this first part we're going to look at the carbohydrates, and I've got some information that I want to go over on the board behind me. Carbohydrate stands for the components that you find in it, which is carbon, hydrogen and oxygen. Now in a carbohydrate, these three elements are found in a specific ratio. So I'll put it up on the board here: carbon, hydrogen and oxygen, and the ratio is 1, 2, 1. So every carbon you have 2 hydrogens and 1 oxygen. Carbohydrates are used as a source to produce energy. And in the cell, the energy, as we're going to look at in just a couple of talks' time, is adenosine triphosphate, or ATP. Now, it's a common misconception that glucose is the energy of the cell, and it's not. It's one of the things that can be used to create the energy of the cell, one of the things that, if you like, can recharge the battery. So the glucose itself is the starting point, but so could be a fat. Even a protein can go in there and be used to make energy. The only thing that carbohydrates do for us is allow us to produce ATP. They don't have any other structural role in the human body. So in our diets we consume carbohydrates, or carbs, we consume fats, and we consume protein. And these are our major macromolecules that we consume. We also actually consume nucleic acids, because we consume living organisms which have nuclei in them containing those nucleic acids. But we don't essentially use them in the same way as we use the other three. The proteins are the building blocks of our entire structure. And the fats help with that structure, but also are, as we'll see, capable of giving us other properties as well. But we're with the carbohydrates just now, so we'll stay with that. We'll just look at some basic parts. So, carbohydrates, we can have monomers and polymers of these carbohydrates. What does a monomer and a polymer mean? The monomer is the basic unit that they can be broken down to. Now in the carbohydrate world, there's a lot of different possibilities, but I'm going to stick with the main two that we actually come across in our diet. And that would be glucose and fructose. These are the two monomers. So once you break down a large piece of starch, you get glucose, but if you break down table sugar, for example, you get one molecule of glucose and one molecule of fructose for every molecule of sucrose. So these are our monomers. This is what can be absorbed in the gut and enter into our blood. These can also enter into our cells. They can be joined together to create larger molecules. As I said, you join this with this and you get sucrose, which is table sugar, And then if you just took lots of glucose and joined it to itself, you'd get things like starch or glycogen, which we use to store glucose in our own muscles and liver. Or if you change the linkage of how they're joined, you can get cellulose, which is the building block of plant matter, such as grass. So our polymers are created by a straightforward chemical process called dehydration synthesis, or DS. Dehydration synthesis is where you join two molecules together. Let me hold these two here. You join them together by drawing off a molecule of water, a hydrogen from one side and a hydroxyl from the other. So that's why we call it dehydration, because you're removing water. Synthesis, because we're making two things joined together and making it a whole. So this process, in terms of carbohydrates, creates what's called a glycosidic link. And that's really a carbon of the glucose, for example, joined to the carbon of another glucose or a fructose, for example. In between there is an oxygen molecule. And this is the glycosidic link. Now between glucose to glucose, and I've drawn these structures in a linear fashion, but they actually exist in a ring structured pattern, and I'm not doing that accurately, so don't learn that. But between one and the other, the oxygen, for example, sitting here and joined to the carbon here and here, carbon 1 here and carbon 4 here, so we call it an alpha 1,4 glycosidic link, and that's between glucose and glucose. If you have lots of these, you end up with something called starch or glycogen. Now if you join glucose to fructose, the fructose is a different structure, as we can see here. You've got the same amount of things inside it, so both of these hold that ratio of 1 to 1. So there are 1, 2, 3, 4, 5, 6 carbons, so carbon 6. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And we have 1, 2, 3, 4, 5, 6 oxygens. And that's your 1 to 1 ratio. C6H12O6. Let's look at fructose. 2, 3, 4, 5, 6 carbons. 4, 5, 6, 7, 8, 9, 10, 11, 12. And then oxygens 1, 2, 3, 4, 5, and 6. So, again, the 1 to 1 ratio, and the carbohydrate is maintained. Notice that they actually have the same chemical formula, but they are structured differently. Whereas the double bonded oxygen on glucose is at the tail end of this group, it's actually on the second carbon of this group. That means that, it means a couple of things actually. Glucose and fructose, although they're chemically the same amount of carbons, hydrogens and oxygens in them, because of that slight change in their structure, makes fructose many times more sweet than glucose is. And that's why it's commonly used in the food industry to add sweetness to things, because you don't need too much fructose to make something taste very sweet. The other aspect is how they're actually absorbed. We're going to talk about that later in the course in physiology. We're going to look at GLUT4 transporters when we talk about the endocrine system. But just mark it just now that glucose and fructose are absorbed differently. They have different carriers to take them in and out of cells. And we're much better set up for dealing with glucose than we are with fructose. And there's a lot of research going on just now to truly understand the consequences of that difference, because we do now consume a lot more fructose than we ever used to, and that potentially has health consequences for us. But we'll talk about that later on in the course, and by all means ask any questions that you have about that. So we've got our monomers here. Polymers, glucose to glucose to glucose through an alpha 1,4 gives you starch and glycogen. Glucose to fructose, because of the different structures, is an alpha 1,2 glycosidic link. And cellulose, which is that backbone of the cells in plant matter, is a beta 1,4. So still a 1,4, so still a glycosidic link, very similar to what makes starch and glycogen, but a slightly different version of it and how they set themselves up. In the beta 1,4 link, we do not contain the enzyme that breaks that link, and we'll talk about enzymes in the next next two groups, because we're going to do cell transport next, and after that we'll talk about enzymes. So we don't have a specialist protein to break this link, and we don't contain bacteria that can also do it, unlike cattle and sheep, which have rumens, etc., and they actually have the bacteria in there which can break this link and therefore give them the glucose from it, and therefore they can mostly exist on just eating grasses. So that's really all I want to say about carbohydrates. They're made of carbon, hydrogen, oxygen and a 1,2,1 link. Their monomers are what we absorb in our gut. There's many different types, but we've looked at glucose and fructose. There's also lactose in milk, there's galactose, etc, etc, etc. And then we can join them together. I'll just put one in the middle. If we just join two together, like table salt, we end up with a dimer, which is 2, so that would be a glucose joined to a fructose, which is table sugar, and I apologise if I just said salt, because I've got salt on the brain just now. So table sugar is a dimer, you break it in half, you end up with, you break that to that and that, and if you join something by dehydration synthesis, you break it by adding back the water, and that's called hydrolysis. Lysis means to break, and hydro is water, so you break by adding water. So it's called hydrolysis or hydrolysis is the correct pronunciation. So we've got our monomers, our dimers, our polymers, and that's what we call the complex carbohydrates in our dietary things. So things like bread, wheats, etc. have glucose in them, but they're in the form of starch, and then we have to break that down and release the glucose. Whereas something like table sugar is much simpler. The sugar hits our blood very, very quickly. And if you've ever been around children that have just been given a large bowl of ice cream, which is basically sugar, and then observe them for the next hour, they're kind of running around and screaming and etc, because they're hyper, because they have a sudden hit of sugar. And then of course we release the insulin, and all that sugar leaves the blood, enters the cells, and they go crash down. Okay, so that's everything I want to say about carbohydrates. Those are the main cliff points. I'll be back, and the next one I'm going to talk about will be lipids.